And today it's our great pleasure to have Dr. Roberts to give us a talk on carbon capture technology development in Saudi Arabia. And Dr. Roberts is my former colleague at NC State. And so he received his PhD from University of Michigan under Dr. James Driscoll. And then he started spent 2 years at NASA Langley working on scramjets. And then he joined NC State, so where he got his professorship. And he also was a director of the Applied Energy Research Lab back to 2011. And then he started at KAUST at CCRC, and where he's currently the director of CCRC. And CCRC is actually one of the world's largest and the most productive combustion research center in the world. And I visited there a few times. It's quite impressive. And Dr. Roberts also received quite a few of awards, including the NSF Career and the Army Young Investigator Award. And currently, he's also a fellow of Combustion Institute and also some other roles. And so under his leadership, I think the center is growing pretty fast and very impressive recent years. So with that, we welcome Dr. Roberts to give us a good talk on carbon capture. So go ahead, Dr. Roberts.
Thank you, Taegong, for the very nice introduction. And thank you, Professor Ju and Professor Sun, for the kind introduction, for the invitation to give this seminar. So carbon capture certainly is very much in the headlines. I would like to talk a little bit about some of the activities that are happening here in the kingdom that may see application worldwide, but certainly are relevant to the fuels and the heat engines that we have here in the kingdom. So I'll set the background. Most of this will be review. So why CO2 capture? The circular carbon economy. This is an output from the most recent G20. I'll talk a little bit about some of the alternatives to carbon capture, set the landscape. And then I'll talk about two technologies that we're working on here in the center. One, cryogenic carbon capture, which seems a little bit silly to talk about cryogenics in the desert, but hopefully I'll convince you that it makes sense. And then calcium looping. Now we are doing other work at KAUST outside of the center in non-point source, so natural carbon capture, say in mangroves and the root system of mangroves, as well as direct air capture, but I'm going to limit this on point sources. So, one good measure of the impact of human activity is the cost of weather events. So in last year, there were 22 separate multi-billion-dollar weather and climate disaster related events. You can see them listed here. And these 22 events cost insurance claims a total of $95 billion. So it's a expensive proposition if we don't get a handle on this. Here I'm plotting the growth in a single calendar year of the damages over a 40-year period from 1980 to 2022. And you see several highlighted there. And 5 of the 6 most expensive years have occurred in the last 5 years out of the last 40. And there's no reason to suspect this is an anomaly and this trend won't continue. So there's a lot of money being wasted by not tackling this problem. Okay, so most of you have seen this plot or similar plots, and so it's the energy produced by various fossil fuels, and you see where in this region, renewables over the next 25, 30 years will continue to increase as primarily coal decreases, oil will remain essentially the same, and gas will remain essentially the same in a business as usual type environment. To reach Paris Accord, the 1.5 degree path, we have to dramatically reduce the CO2 output. Even the 2 degree, which will have catastrophic consequences, we have to dramatically reduce the CO2 emissions and start pulling it out of the air. So this is the same plot. So this is the carbon emissions per year. This is business as usual. This is a reduction in CO2 emissions annually through efficiency improvements. This is the low-hanging fruit. This is due, this gain, potential gain, is due to energy mix, fuel switching, primarily moving away from high carbon-hydrogen ratio fuels like coal and oil to natural gas. And then an additional amount through carbon capture and sequestration. This is the 2 degree line, and this is the 1.5 degree or net zero line. This is the energy mix. You see that oil will decrease dramatically. Coal will virtually disappear. Natural gas won't change much, but of course the largest growths will be in renewables. So we need to be capturing 5 gigatons per year of CO2 by 2050 in order to meet a net zero outcome. And if you integrate this between now and then, that's 90 gigatons of CO2 we have to remove. A tremendous problem or opportunity. The G20, the 20 largest economies in the world, meet annually. 2020, it was hosted by the Kingdom, so a rotating basis. 2019 was Japan. Next year will be Italy. KAUST was quite involved in the G20 activities. One of the primary outcomes of the G20 are these series of communiques. One of the most important communiques comes from the ministerial meeting of the energy secretaries or ministers. And this year that it focused on circular carbon economy, energy access, energy security, and market stability. So this is a direct quote from the communique. We acknowledge that the CCE, circular carbon economy approach, is a holistic, integrated, inclusive, and pragmatic approach to managing emissions. So you can read the rest of the quote. I'd like to say that this was the first time in the history of the G20 that all countries approved all elements of the communique, which is not trivial when you look at the different needs and objectives of the 20 countries. Another quote: building upon previous comments by the energy ministers and past presidencies, we endorse the circular carbon economy platform and its 4 Rs, which are reduce, reuse, recycle, and remove. So an extension of the circular economy of reduce, reuse, recycle. So in this context, reuse is converting emissions into useful industrial products by deploying carbon capture and utilization, and remove emissions from the atmosphere, as well as heavy industries and facilities through direct carbon capture and storage and direct air capture. So hopefully many of you seen this. Bill McDonough came up with this circular carbon economy concept several years ago. He's identified carbon in 3 different categories. Fugitive carbon, which is the carbon that's anthropogenic, so coming out of the ground and ends up in the atmosphere or ends up in the ocean, either as CO2 or some non-recycled plastic. We have durable carbon, which is the material that's in use, that's being constantly recycled, and then living carbon, which is the CO2 that gets absorbed and converted into plants, animals. And I like his quote. He says, carbon, the element, is not the enemy. Climate change is the result of breakdowns in the carbon cycle caused by us. It is a design failure. In the right place, carbon is a resource and a tool. So I think the combustion community is well posed to convince the audience that this is true, that this is a design problem. It's not a catastrophic, irrecoverable consequence, but it's a design failure, and we can fix design failures. So this is a plot that Ahmed Kowater, the CTO of Aramco, put together, showing these various 4 R's. So here we have CO2 coming out of the ground in the form of a fossil fuel, gets converted to chemicals or hydrogen, or it gets combusted, releasing CO2. The CO2 then can be removed through natural solutions and either put back in the ground, enhanced oil recovery or sequestration. It can be used to produce synthetic hydrocarbons. It can be reused or it can be recycled. And the difference between reuse and recycle in this context is reuse, the CO2 is not changed, the chemical form is not changed, or in recycle, it is changed. So you can think about perhaps as we move towards a hydrogen environment, you'd like to take advantage of a liquid fuel distribution system. And so you might think about synthesizing, say, methanol or ammonia with this hydrogen. And if you're going to synthesize methanol, you need CO2. Okay, so NEOM, maybe some of you have seen this. I encourage you to take a look at the link. This is this $500 billion city of the future that's planned in the northwest corner of the kingdom. The kingdom wants to be a global leader in hydrogen production and use, and NEOM will be leading this effort. It will be the home of the largest green hydrogen facility in the world. They project 4 gigawatts of solar running electrolyzers in this Helios project. They're breaking ground now. They have 20 megawatts that's going in now. The vast majority of hydrogen currently is produced by steam methane reforming. So here you see the equation. You take methane in the presence of water, heat it, catalyze it, and you can form a lot of hydrogen and CO2. If the CO2 is released to the atmosphere, then this is now called brown hydrogen. This is about 97% of the hydrogen produced is brown hydrogen. However, if you capture the CO2 that you liberate and sequester it, then it's blue hydrogen, which has an advantage, of course. Blue hydrogen is seen as a bridging technology to the goal of green hydrogen. Green hydrogen is hydrogen produced primarily from the electrolysis of water, where the electrons come from solar or wind. So this bridging technology is designed to allow time for the H2 infrastructure to be developed. So hydrogen and CCUS are keys to a circular carbon economy. There's been a dramatic increase in the interest and funding, and certainly in the US, this is going to, I think, increase dramatically with this administration. But even so, there's $16 billion committed through various announcements, even during a pandemic, and the United States not really participating in CCUS activities in the previous administration. So, of course, you can't pull the CO2 out for free. Right. And so there's work associated with separating gases. So here I'm plotting the amount of work, the minimum amount of work required to separate CO2 from a bath gas. Of course, the amount of work goes down as the initial CO2 mole fraction increases, and the amount of work goes up as you try and pull out more and more of the CO2. So I've got several heat engines listed here. Cement happens to be one of the lowest because it has a high CO2 mole fraction in the flue gas. Then you've got steam methane reforming, another low-hanging fruit. Heavy fuel oil fired steam boilers. So this is a boiler with a steam turbine. Natural gas combined cycle has low CO2. And then, of course, trying to pull it out of air at 400, 450 ppm is the most expensive. Additionally, you have to do something with the CO2. If you're going to compress it for EOR or liquefy it to pipe it in in a pipeline, then there's an additional penalty of compression. So some of the various technologies, you can pull it out, post-combustion, pre-combustion, or oxy-combustion. So post-combustion, burn your fuel in air, take your flue gas, and then separate it. This is the most common technology now. Pre-combustion, use a air separation unit. And pre-combustion, you gasify it, take the syngas, so you gasify your fuel to CO and H2, or CO2 and H2, separate these, burn the hydrogen, and you get CO2 lean flue gas. And then oxy-combustion, take the air, separate it, the oxygen from the nitrogen, and then you burn in an oxygen environment, making the CO2 separation much easier. So some of the advantages and disadvantages of pre-combustion, major changes to the plant, changes to the combustion system, advantages, low volume of flue gas, and the mixtures are binary. So again, going back to the minimum energy of separation, it's much cheaper. And then you can deal with high concentrations of CO2, and gas can be maintained at the desired pressure. In post-combustion, needs minimum changes for retrofit, and no changes to the combustion system. It's bolt onto the back end, but you've got a lot of flue gas. It's mostly nitrogen, so this requires large equipment. The gas also typically involves other pollutants, criteria area pollutants, NOx, SOx, perhaps ash, soot. Concentrations are typically lower than with pre-combustion, and the gas is always at atmospheric pressure. So this is a snapshot of the technology readiness level. You see a whole spectrum of technologies. We're a university, we're working on the left-hand side here. So this third generation mineralization, biosequestration, cryogenics you see here, and then direct air capture CO2 scrubbing are very much at the research early deployment scale. These are some of the major programs. We certainly expect these to be picking up in the near future, but these are the active projects now. I think one of the most popular or well-known examples is Petronova. So here you see it, and you see the capture unit is a large fraction of the physical plant. So this uses an amine system where you absorb it and then scrub the CO2 out of the amine, and the amine is recycled. So this is an energy penalty. Just last week, or earlier this week, this Petronova plant is closed indefinitely. So other technologies that are evolving, so chemical looping, where you use a metal to transport oxygen, calcium looping, which I'm going to talk about, I hope, absorption, which is a second generation amine-based system, and you can have temperature swing or pressure swing absorption, and then membrane separations. So you need the right membrane, and you need a delta P to get the membranes to work. Okay, so carbon capture. So the CO2 efficiency really depends solely on the temperature. So the partial pressure of the CO2 can be expressed in the solid vapor equilibrium and this empirical equation. CO2 is well behaved in that the triple point is accessible in terms of temperature and pressure. So you can choose based on the CO2 content in your flue gas and the capture efficiency, what temperature you need to operate at. So of course, the lower the temperature, the higher your efficiency based on this relationship here. The higher your CO2 content, the warmer it can be and still capture CO2. Okay, so with this technique, you could think about direct air capture, but you're way down here, and so you have to be considerably colder. So in this example, a 15-degree temperature drop increases the efficiency from 90 to 99%. So the penalty you pay is in how cold you make the gas, and that dictates how much CO2 you are able to extract. So there are several different cryogenic technologies. This is the one I'm going to talk about in some detail. There are other technologies. In this case, you take steel balls and you freeze them or cool them cryogenically. You drop them through counter-propagating flue gas. The CO2 freezes onto these balls. You then heat the steel balls up. The CO2 comes off, and then you cool the steel balls back down. A similar technology here, but this is a packed bed rather than a moving bed. And in this case, you allow the CO2 to freeze out on the surface on a heat exchanger. This typically is a problem, but then you have multiple heat exchangers and you alternate between heat exchangers. And so one of them is freezing CO2 out, and while the other one is being warmed and enough that the CO2 boils off or sublimates off. Okay, so the technology that we're working with, and this was invented by Larry Baxter at SES, somebody well known to the combustion community. So SES is his company. You take the flue gas, you cool it down to cryogenic temperatures, the CO2 desublimates out as a solid, which makes it easy to compress and liquefy. The CO2-free air comes back, and the penalty you pay is in cooling, and but the vast majority is in how good your heat exchanger is. So I'll go through this in a little bit more detail. We believe the OPEX and CAPEX are much lower than the competing second generation amine system. There's no regenerating of the amine, so there's no steam or heat source. You're able to recover the water from the flue gas. There's no real degradation of the working fluid. I hope to show you that we can capture criteria era pollutants, NO2 and SOx, not NO, but NO2. These liquefy out at these temperatures. I think there's fairly easy integration of renewables, and it's bolt on in the back end. So the next few slides go through the process in detail. Here you see the smelter. So the flue gas comes in, it gets dried. The CO2 gets desublimated out, comes out as a slurry, goes through this path, gets compressed, melted, and then comes out. I'll go through these in detail. This is the solid CO2 coming out when it's running in an open environment. Of course, it's typically closed. And this is a mixture of liquid and solid CO2. This is the melter. One of the things that's important is the input is electricity, and that's to drive the Stirling cryo coolers. And so it's quite amenable to integration with the renewables. And you could think of storing the refrigerant, this liquid helium or liquid N2, in mass as a means of energy storage for using this off-peak. Okay, so the flue gas, so I have the pressure temperature diagram over here, comes in, gets dried. We can't tolerate water in the recuperator because it will freeze out on the surface. So we dry it, cool it a little bit, comes in, goes through a recuperator, gets cold. The majority of the temperature change occurs in the desublimating heat exchanger. Cold, CO2 free gas comes out, goes back to this multi-element heat exchanger, comes out warm, and then is exhausted. So it's basically, we take it warm, cool it off, and then bring it back. All right, so this is primarily the nitrogen gas path. The CO2 path comes out, goes to the dryer, cools off a little bit, goes to the recuperator, cools off some more, goes into the recuperator, into the desublimating heat exchanger, where a cryogenic liquid is sprayed down through this counter-propagating CO2-laden gas. The CO2 freezes on the surface of these droplets. These droplets fall to the bottom in a slurry. The slurry is compressed, goes through another heat exchange with the cryo cooler. It is then separated. This solid CO2 is separated from the liquid contact refrigerant. It's melted, compressed again, goes through this recuperator where it's warmed back up and then is pumped out. So the advantage is you've got CO2 at 100, 200 bar room temperature, and the compression has all been done either as a solid or a liquid. So you save that 150 kilojoules per kilogram of compression costs, because compressing a liquid is essentially free. Okay, so again, we can choose how much CO2 we want to pull out, the capture efficiency, and we can handle multiple CO2 content streams based on the temperature. The CO2 is desublimated between 100, 130 C. It's transported as a slurry, and then the slurry is squeezed out through this screw press. It's smelted to -30 and then pumped to 100, 200 atmospheres for storage. So this is the basic process. Does it make sense? So we did an analysis on flue gas coming from a cement kiln. So here you see the composition. And SPECA is a standard means of understanding the energy consumption of the CO2 avoided. So we compared these to several different technologies. So second generation amines, oxyfuel, calcium looping, membrane assisted liquefaction, and then cryogenics. And you see that this turns out to be the cheapest. The carbon capture, the cost to separate this is 0.72 megajoules per kilogram CO2. Again, this is for a 2,000 ton a day scale, and this assumes a 45% efficiency. So this has been tested at several different plants. Here's the Pacific Corp coal plant. We're just pulling a small piece off the stream. This is the CO2 capture. So it's 98% capture over many hours. And this is the temperature. So you see fluctuations in the temperature, but this is basically running steady state. And we can capture with this rig about a ton a day. So some of the things that we're working on now is trying to understand how to maximize this desublimating heat exchanger. So again, we've got flue gas coming in, CO2 laden flue gas coming in, propagates up. We have a counter-propagating droplets of this contact liquid, in this case isopentane. The CO2 freezes, desublimates on the surface. So we're developing desublimation models. Of course, the characteristics of the droplet, the heat transfer characteristics, the Stokes number, the whole behavior of the droplet changes as it's propagating through this CO2 varying stream. We don't want carryover. We want small droplets to generate surface area, but we don't want isopentane leaving with our clean gas. So there's a range of droplets that we want to try and match or try and obtain. So that means we have to understand the droplet breakup behavior. So again, characterized by Weber number, Onsange number. So this is standard stuff. The Weber numbers that we're typically going to be dealing with based on our perceived droplet size, gas composition, and velocity are going to be in this range where we're talking about vibrational bag, backup, bag breakup, and multi-mode, depending on the velocity and the droplet size that we have. So we're also interested in the jet, how the jet breaks up. So we're interested in the droplet behavior and the jet breakup behavior. So again, this is pretty textbook stuff. These are some simulations that Hong Yim and his group have done. Here these are isopentane at cryogenic temperatures and a nitrogen bath gas, and you see the effect of swirl in the jet without swirl, very slow breakup, and then a lot of too much swirl, and you have this sheet formation. So with these kind of models, we can start to custom design the injection to, again, maximize the droplet size distribution that we want to capture the CO2 without losing refrigerant. We're also interested in pollutant capture. So in this dryer right now, it's a molecular sieve, or you can use things like a a membrane. But what we're interested in being able to pull out SOx and NO2 as well as PM and water at the same time. So you could think about another contact liquid heat exchanger where this stuff, the water freezes on the droplet surface, but the CO2, the SO2 and the NO2 liquefy out and are captured. So this is what we're working on. The kingdom burns a lot of high sulfur fuel and has a lot of sour gas. So SOx is very important here. So this is a piece that we're looking at to bring this technology here to the kingdom. This is our roadmap. So this 1 ton a day system is being moved to Saudi Electricity Company, which is up the road from us, where we're going to run this at 1 ton a day from a heavy fuel oil fired power plant. And we are going to demonstrate the simultaneous capture of SOx, NOx, and PM. And we're just starting a feed front-end engineering design program for the next 6 months, working with NEOM and Chart Industries that has acquired SES to build about a 30 ton a day system. And this is going to feed a methanol synthesis plant with the H2 being generated by the Helios program. Okay, I think I'm running short on time, so I'll go through this quickly. We wanted to look at calcium looping, primarily the role of SO2 on calcium looping. Again, we have very high SO2 exhaust streams here. The HFO that we burn in several power plants is about 3.5 to 4% SO2 sulfur. So calcium looping. We use calcium oxide. It reacts with the CO2 and forms calcium carbonate. And then this calcium carbonate is regenerated in a calciner. So we have the capture CO2 and calcium oxide forms calcium carbonate. So we have this CO2 depleted flue stream. The calcium carbonate goes into a calciner where we have to heat it up. This is where we had enthalpy coming out of this. So we need an air separation unit. Coming out of this, we have CO2 and H2O and calcium oxide. And so this is the loop. Calcium oxide gets converted to calcium carbonate. CO2 gets driven off in the calciner. So capture and regeneration. Turns out that calcium carbonate will also absorb SOx, SO2, and form calcium sulfate. And this calcium sulfate then can be captured and we purge this out. So we want to understand what's the role of the makeup of the limestone on its ability to capture SO2 and not be poisoned by it. So this is a timeline that's been around for more than 100 years, but it's only recently, last 20 years, been looked at for carbon capture, and only very recently for being looked at for simultaneous SOx and CO2 capture. So this is a multi-scale approach. So some modeling with Aspen, a 7 kilowatt bubbling fluidized bed reactor, looking at the results with the thermogravimetric analyzer, and then exploiting these in the rig at Stuttgart, where they have a 20 kilowatt dual fluidized bed, and then looking at the details of the calcium carbonate. So we looked at 3 different limestones. We used German limestone as the baseline, Riyadh limestone, and Sabra limestone. So this is essentially marble. And this is particularly germane because it's the West Coast where all the high sulfur burning power plants are, because of the lack of natural gas. So we examine the capture behavior of limestone-derived calcium oxide, and then we wanted to understand what's happening with this. So we came up with an experimental metrics looking at steam content, SOx content, simultaneously and individually, and then looking at different space times. We were able to come up with an experimental reaction rate kinetics, and these do very, very well with a theoretical assessment for these different limestones. Here I'm plotting the capture efficiency, CO2 capture efficiency versus the calcium oxide conversion, and you see two regimes, a diffusion limited regime and a kinetic limited regime. So these are the two sorbents, the rheod and the subar, the marble. The effective H2O or OH is quite different between these two. So the OH enhances the rheod but is detrimental to the marble. Conversely, the SOx is very detrimental to the rheod but had virtually no effect on the marble. And then the combination of water and SOx was kind of the average, but really more favored the influence of the water. And looking at the time, you see that at short times the SOx is detrimental, but at longer times it's actually beneficial for the marble. So why is this? So using TEM and SEM, we were able to go in and look at the pore structures. This is the rheod limestone, and this is the subar, the marble limestone. So the rheod structure is typical of limestone, and subar is typical of marble. So the marble's discrete monolithic monomineralic phases lead to narrower and more structured pores. So you see this clearly in the picture. So it's more prone to blockage. The blockage is exacerbated by OH catalyzing carbonation. The limited calcium sulfate pacifies the reactive surfaces. And so this calcium sulfate counteracts this OH star or OH radical catalyzing effect. So the sulfation preserves the marble porosity, which is why we see it as being beneficial in the marble, but detrimental in the traditional limestone. So we wanted to try and capture this effect. So Sally Holmes, the PhD student that did this primarily with Bob Dibble, introduced this term sulfation deactivation factor in this equation for capture capacity to try and predict the behavior of this sulfation. So here she's plotting the maximum conversion capture capacity versus equivalent number of cycles, and you see the two different limestones, traditional limestone here and the marble here, and based on the equivalence number, you're in a this A factor is approximately 0 at low equivalence cycles, and becomes a function of the phase time when Xn is less than the carbonation mole fraction. So the main energy penalty is this air separation unit. As I said, you can calculate the amount of energy required by looking at the enthalpy of conversion and then the CCP delta T for the different components. We can express these ratios in terms of looping ratio and makeup ratio. And so you can plot the efficiency penalty. So you want lower is better. These are different makeup ratios. So you'd like, of course, a low makeup ratio. This is constrained by this X of N. So this is a CO2-free flue gas. This is, if we introduce SOx into the carbonator, you do see a penalty. You see less penalty with the subar than you do with the rheod. And if you introduce CO2 into the carbonator and the calciner, you pay a very large penalty with the rheod, but again, a very small penalty over quite a range of mass ratios and looping ratios in the subar marble. So the efficiency drop due to co-capture of SO2 is competitive. Synergy with industry, mainly cement, is recommended to increase the process sustainability. This stuff is cheap. It's a lot of mass you have to move, but it's cheap. And so, we'd like to try and use it. And this is pending a full techno-economic study and life cycle analysis. Concluding remarks, SOC's co-capture potential makes cryogenic carbon capture and calcium looping promising for the kingdom, again, where we burn high sulfur fuels, and rapid scaling to the billion ton a day is needed if we're ever going to get close to this 5 gigaton a year target. And you see lots of activity. Earlier this week, ExxonMobil said $3 billion they're going to invest. Qatar, of course, Elon Musk is putting some of his money towards this. So it's happening. Some quick acknowledgements. The KAUST near-term grant challenge for the cryogenic carbon capture. Again, Sustainable Energy Solutions, Larry Baxter's company, has done all the hefty lifting for this cryogenics, and they were recently acquired. And then the CCRC for my time. This is the team. I think you all know Bob Dibble. He is very much responsible for getting us involved in both of these projects. So I'd like to thank him. Hong is handling the simulation. The calcium looping was mostly Sally's work. And then the SES leadership team. So with that, I'll say thank you and answer questions.
Okay, thank you, Dr. Roberts. It's very interesting and good work there. It's a very new area for the combustion community. I think it's very good and instructive. So far I got two questions from two members. The first one is from Dr. Atkin, and on slide 28. What are the criteria to select ISO patent for the droplets?
A liquid with a low CO2 solubility. That's a liquid at these cryogenic temperatures. And isopentane turns out to be a very readily available, low cost, essentially non-toxic liquid. It does have issues in that you have to be careful what your O2 content is in your flue gas. These are cryogenic temperatures, but you always want to work in trepidation when you're mixing a hydrocarbon with oxygen. So we are interested in trying to identify other suitable contact liquids for high O2 content flue gases. But this was the reason: low CO2 solubility and a liquid at these cryogenic temperatures.
Okay, good. Let's next question from Dr. Albana. It is interesting to see breakup mechanism in counterflow of CO2. I wonder which platform was used to perform simulation. I noticed how severe the temperature is low during CO2 capture, requiring refrigeration. From environmental and economical point of view, how can we access the efficiency of the process?
Yeah, so it's a bit counterintuitive, right? Because these are very low temperatures, and you're taking a hot flue gas, but it's really all about heat management. Right? So as your heat exchangers get good, this process gets cheaper and cheaper, and really what you're trying to do is it's virtually the same as an air separation unit, but now you're separating CO2 from N2 instead of O2 from N2, which is much easier, basically, right? Air separation unit uses cryogenics. You have to be careful in this because you don't want to use traditional heat exchangers because the CO2 desublimates and frosts the surface. And so this is why we have to go to a contact liquid. The thermodynamics are sound. It is cheaper. It is about half the cost of an amine system. because you don't have to regenerate the amines. You don't have to replace the amines. As the CO2 content in the flue gas goes down, you have to get colder, right? So this is the penalty you have to pay. So this isn't going to be the solution for all systems. I think it works potentially quite well for a combined cycle where the flue gas is already cooled because you've extracted enthalpy. Certainly will work well for high CO2 content streams like steam methane reforming or cement kiln. I think, although you can do it, I think it's very challenging to get to temperatures required for direct air capture.
May I ask, could you perhaps comment also on the Stirling engines you're using for refrigeration? How large can they be? Or are they already running well with the sizes you need?
So they're not running nearly as well at this scale as they would at the 1,000 ton a day, 5,000 ton a day scale. The cryo coolers get more efficient at scale, as well as all the pumps. So we're not anywhere near the $40, $45 a ton capture cost we think we can get to at this scale. There will be economies of scale. And this is, I think, is going to accelerate now with the acquisition of SES by Chart Industries, who specializes in cryogenics and heat exchangers.
Okay, thank you.
Okay, I think the question, what kind of platform was used to perform the simulation?
So these are open foam. I should say this desublimation on the droplet is a little bit artificial because it's not truly desublimation. It's a very viscous liquid condensing on a different liquid. Oh. We're still figuring out how we do the desublimation, and I think it's going to be very interesting. You know, there are simulations of ice formation on wings of aircraft, say, but we haven't found any simulations of an actual desublimation process at these kinds of, well, at any temperatures, but let alone these temperatures where properties are not well known.
So next question from Dr. Gore, and are there some studies of scale at which it works? And cement clean came to 500 megawatts utility power units. You might see the question there.
Yeah. So we certainly have done, and primarily SES have done studies to look at how this scales up, and scaling to 5,000 tons a day, 8,000, 10,000 tons a day. Everything gets easier as you go to the large scales. Again, we're doing a feed on a 30 ton a day. This will be the next size that we produce, but I think going to several thousand tons a day will not be, is not where the real challenge is. This cement kiln that we're interested in working with is putting out 4,500 tons a day of CO2. So we'll be capturing less than a percent of the CO2. But I think it's very scalable. I think this is a hard scale, the ton a day scale.
Well, I have one question, Bill.
Yes.
So in terms of a scale up, right? You have that the oxy air separation to oxygen and nitrogen. Of course, that you need lower temperature to separate that, and then the other way that you need to do a big chiller, and to separate CO2. In terms of a scale up technology, which way that they already developed that for example, we talk about megatons per day or per year. So
yeah, so like Air Products, who builds ASUs, that's all based on cryogenic refrigeration. So building large scale cryogenic minus 145, 160 degree heat cryo pumps is not really a challenge that's commercially viable. For example, in the Jazan IGCC, Integrated Gas-Fired Combined Cycle Plant, it's the largest in the world, and this is owned by Air Products. So these ASUs, this is essentially air separation unit cryotechnology, but have been very clever with the final heat exchanger in that it's a contact liquid to prevent the problem of fouling on the surface.
So how does this technology compare to these days? A lot of people talking about the supercritical CO2 cycle, right? You can raise that the pressure to supercritical water, and then you can separate that the CO2 and water downstream, and then the cycle efficiency can get to 50-some%.
Yeah.
So how does this technology compare to the other one?
So one of the big costs, of course, is getting the CO2 to those temperatures and pressures.
Okay.
Right? And so that you're compressing a gas, which is expensive. One of the advantages here is we're compressing it already as a solid first and then as a liquid. So the compression costs are trivial. And depending on what the downstream use is, if you're say interested in sequestration or EOR, you need at least 80 atmospheres. And it's fairly easy to clean. So you can put on a distillation column on the back end of this to clean the CO2 to get it to pipeline purity requirements. So I think the big problem with supercritical CO2 oxy-combustion is, again, you got to compress the CO2, and you're still paying on the front end to do the separation of the air, right, to run an oxy-combustion. And so you're separating O2 from N2 instead of CO2 from N2. And it's much easier to separate CO2 from N2 than O2 from N2.
So Dr. Gore has a follow-up question, more general. Educational updates to ME curriculum that you would suggest for the new power generation systems that must include CO2 capture. It's a question to ask you. Any suggestions on that?
Yeah, I think that's great. We certainly need to be including and talking about carbon capture technologies in our undergraduate and first year graduate level courses. This is not going away. I mean, I think now with this administration, virtually everybody agrees that carbon capture is essential to meet the Paris Accords and meet zero net carbon. I mean, 5 gigatons of CO2 annually we have to pull out. It's going to take a lot of bright people working on this. And so I think we need to enthuse the young people, convince them that this is a viable long-term problem that requires their talent.
I agree. It's a big economic challenge with so many coal burning power plants shutting down these days in North and South Dakota and many parts of the United States. Economic challenge of coal producing counties and states are very serious.
Yeah, you know, the kingdom is interested, of course, in being a leader in hydrogen, but they have 450 gas turbines. They have 50 gigawatts of installed capacity burning heavy liquids. You know, it's going to take a long time to replace that infrastructure, and that's not unique to the world. So we need bolt-on technologies. We need bridging technologies. We need scalable technologies. We have to get there, but we have to have a pragmatic pathway.
You seem to indicate that the first cost advantages of these technology exist over amine technologies and so forth.
Yeah, we believe that we can, at scale, get down to less than $40 a ton capture.
Very much, Bill, for the kind of talk. Actually, I have one question.
Yes.
That I would like to ask you. So in average, what is the ratio of the energy needed for the carbon capture and sequestration to the energy released for that generation of the CO2 through combustion?
Yeah, so typically when you talk about an amines-based system, you're talking about an 18 to 20%, maybe 23% energy penalty, right? And this energy penalty is half that. So we're down in the 13, 14, 15% range.
Okay.
Yeah, so that's another good measure.
So that actually means when we capture that carbon, we actually released a little bit more CO2.
Correct.
Probably.
You have to capture a little bit more, yeah.
Yeah.
Yep.
Thanks. Well, I think, you know, the idea is very exciting if it's for the power generation purposes, where you can do a global control of the CO2. Mm-hmm. But for these ground transportations, you know, for the IC engines, how can we actually improve the carbon capture?
Well, so one model is that ground transportation, personal transport, is going to be fully electrified. Marine transport, you could think about putting a cryogenic system on a ship because you're storing the CO2 as liquid and not paying the compression costs. And then for aviation, you're going to have to do direct air capture or convert them to hydrogen, right? So this is kind of the model that is being proposed within the kingdom, that passenger transportation, that point sources is carbon capture, passenger fleet is electrification or hydrogen, trucking will be eventually hydrogen, and then and marine will be either local carbon capture, perhaps ammonia. There's a lot of people looking at ammonia as a fuel for marine transport. And then aviation, I think it's a little hard to see aviation being electrified or going hydrogen anytime soon. So if you say, okay, I'm going to accept that aviation will continue to be hydrocarbons, then I'll just do a capture equivalent using MOFs or some other direct air capture technology.